Welcome back to Statistical Reasoning. We are moving on to the second section of Chapter 5. This time, instead of basic probability distributions, we're going to be talking about binomial probability distributions. Just as the name says, we are going to do things that only have two options. That's what binomial means. We are going to focus. So in order for that to happen, we have to make sure we have four requirements taken care of. So the first one, we have to make sure things are a fixed number of trials. In other words, we have to make sure that we're going to do it a certain number of times and not until something occurs. The second requirement is that things are independent. In other words, the effect of one outcome has nothing to do with the effect of another outcome. The third option is that we only have two categories. That's why it's a binomial. So as long as you can do that by saying something is a success or what you're looking for and something is a failure, what you're not looking for, then we're good to go. The fourth one is that we have to make sure that the probability remains the same throughout the time. You can't change as we go along. Some of the assemblage that we need to make sure that we know, we have S and F for success and failure. The probability of a success is P of S. That's the thing we're focused on. Probability of a failure is 1 minus P, and we use the letter Q to represent the probability of a failure. Those are what we don't want to have happen. We have N number of trials. X is what we're focused on. Are we focusing on it occurring 3 times or 10 times or whatever? And then we have our individual P's and Q's. We won't always write it as a large one, so these are the individual trials that we're doing. And then P of X's are going to be our final answer. So when we're talking about success, we need to make sure we focus on what are we trying to get. So it doesn't have to necessarily mean like success as if we passed a test or we were able to get a raise. Sometimes it might be something that is a negative thing, but that doesn't mean it's not a success, because success is what we're focused on, okay, and failures are what we're not. So if I wanted to figure out how many people or what's the probability of failing a test, that's still a success because that's what I'm focused on. So we have some examples. When an adult is randomly selected with replacement, there is a 0.85 probability that this person knows what Twitter is. Suppose that we want to find the probability that exactly 3 of 5 randomly selected adults know what Twitter is. So first we have to see, does it pass the test? Is it do the 4 requirements? Is it a fixed number of trials? Well, fixed number of trials, let's see, it says we're doing 3 of 5. So it's definitely fixed. Is it independent? Is one thing going to have an effect on the other? It's not, because it is independent. It's not going to affect each other because it's with replacement. Do we have 2 categories? Yes, either they know what Twitter is or they don't know what Twitter is. And then does the probability remain the same? Yes, it does, because they're independent. So with that, it says if it is a binomial, which it is, identify those things. So N is how many trials we have, and in this case N is 5. X is what we're focused on, and they wanted to get 3 out of the 5. P is the probability of a success, so probability of knowing Twitter, and we're saying that 0.85 is the probability of knowing Twitter, which means the probability of the failure would be 1 minus 0.85, which is 0.15. So I have N equals 5, X equals 3, P is 0.85, and Q is 0.15. If for some reason that you were told you weren't doing it with without replacement, that then makes it become dependent instead of independent, because it changes the probability from one time to the next. If for some reason you're doing a sample that is no more than 5% of the size of the population, in other words it's so small, then don't worry about it. You can go ahead and treat it as if it was independent. So here's the formula that we would use to do a binomial probability. So to find the probability, we do n factorial, so remember that's how many times we're doing it. X is what we're focused on, minus n, that difference factorial, and then x factorial times the probability, which is the success and how many we're focused on, and then the failure probability, and then what we don't want to have happen. So given the Twitter example that we'd already talked about, and so there's the numbers that we came up with. Let's do the formula. So probability of getting 3. So probability of getting 3, according to the formula, we do n factorial, so that's 5 factorial, over x minus n. Oh, that's right. I remember that now. I just realized that this slide is backwards. So this right here is actually n minus x. So definitely make that change. That should not be x minus n. It should be n minus x. I forgot that that slide was wrong. Okay, so we're going to fix that in the equation that we're doing now. So it's n minus x, so it's 5 minus 3 factorial. And then it's going to be times x factorial, which is 3 factorial. We then multiply that by the probability of the success, which is 0.85, and how many we're focused on, which is 3, times the failure probability, which is 0.15, and then 5 minus 3 is going to be 2. So we have all this. We can do a little bit of it by hand to make it a little bit smaller. 5 minus 3 is 2 factorial. We still have the 3 factorial, 0.85 to the third, 0.15 to the second. So make sure you find your factorial button on your calculator and that you know what your power button is on the calculator. So when you plug that all in, I got 0.138. So my probability is about 13.8%. You can leave it as a decimal or as a percent, whichever one makes more sense for you. So we have a second scenario this time. It's overtime in football. So we know that between 1974 and 2011 there were 460 NFL football games decided in overtime. 252 of them were won by the team that won the overtime coin toss. Is the result of 252 wins in the 460 games equivalent to random chance, or is 252 wins significantly high? So we're going to answer this question by finding the probability of 252 wins or more in 460 games. So let's go ahead and check our requirements. One, do we have a fixed number of trials? And it is out of 460 football games, so yes. Are they independent? Yes, one game had nothing to do with the next game. Are there 2 categories? Yes, either they won or they failed. And is the probability the same? Yes, from time to time. So if we think about it, we could go ahead and define our letters. So our N is 460. Our P, I'm sorry, wait, I forgot our X. Now, let's go ahead and skip X for a minute. Our P would be 200, oh wait, win or lose, so it's 0.5. Our Q would be 0.5, because half the time we win, half the time we lose. And so, because they want us to do 252 wins or more, really we're going to do probability of 252 wins, probability of 253 wins, probability of 254 wins, and so on, all the way up to 460. So that was how we would have to do that formula by hand. That is not reasonable. It takes too long. So then because of that, we would want to use technology to do that. So on the videos that I've put on Blackboard, there's a video to show you how to do that using StatDisk. So make sure for this type of problem, you go ahead and do that. So problems where you're doing 252 or more, right? It's the ones that are or more that you don't have to do a single number. So using StatDisk, we end up with a probability of 0.0224. So now that is less than 0.05, so because it is less than 0.05, as we discussed in the last section, then it is significantly high. Because if it's remember, if it is less than 0.05, then we count it as significant. Okay? So, devil of a problem. Based on the Harris poll, 60% of adults believe in the devil. So this time we're going to use another option. So besides using the formula, besides using StatDisk, there is a formula in your, or a table in your book that you can use. The table is on page 683. So you could pause the video and grab the table so you can see it. And so we can use that when we have to get an exact answer, which in this case we are, and we have a number that is in the table. So the probabilities in the table, there's 0.01, 0.05, 0.10, all the way up to 0.99. So it doesn't include everything, it only includes some of the most prevalent ones. And in our case, we're doing 0.60. So we're going to find the probability that exactly 3 of the 5 adults believe in the devil. So we know our probability of success is 0.60. We're doing 3 of them. So our x is 3 and our n is 5. So using table A1, hopefully you found that, we're going to go down to n equals 5. Then we're going to slide over. We're going to get x equals 3. Once we get x equals 3, we slide over until we get right below p equals 0.60. And it tells us that that is 0.346. which is the same as 34.6% of the time 3 out of 5 adults will believe in the devil. Now if we want to do the probability that the number of adults who believe in the devil is at least 2, so that means we're doing x equals 2, x equals 3, x equals 4, and x equals 5. So I could do each of those and add them up. So it would be the same idea. Using the chart, we know the probability that x equals 2 is 0.230. We just did 3, that was 346. We would do 4, which is 0.259. And then we could do 5, which is 0.078. We would add those all up. 0.23 plus 0.346 plus 0.259 plus 0.078. So a probability that at least 2 people believe in the devil is 0.913, or 91.3% of the time. Now the only options we didn't do was 0 or 1, so that's the other part of that. That's the failure in this case. So using binomial distribution, we can find the mean or the variance or the standard deviation. We did that in section 1. It just wasn't a binomial, it was any distribution. To find the mean, you do n times p. To find the variance, you do n times p times q, and then standard deviation is simply the square root of that. The range rule of thumb, we're just using the idea of 2 standard deviations away to find out if it is significantly low or high. So in the example that we used earlier, where I told you to go look at the video to make sure you knew how to do the probability distribution for a binomial using StatDisk, this one is just asking us to find the mean and the standard deviation and then use our range rule of thumb to tell if it is significant versus using probability. So first let's find the mean. So the mean is n times p. So n is 460, p is 0.5, so our mean ends up being 230. Our standard deviation is the square root of n, which is 460, times p, which is 0.5, times q, which is 0.5. So it's going to end up being the square root of 115. And so we end up with a standard deviation of approximately 10.7. So those are our mean and our standard deviation. Our range rule of thumb to find that if it is significantly low or high. So we're going to take our mean and we're going to subtract 2 standard deviations. This would tell us if it is significantly low. That ends up being 208.6. It's definitely not lower than 208.6, so it's not significantly low. So now we're going to go the other way and add 2 times 10.7. And we end up with 251.7. I'm sorry, 0.4. So anything above 251.4 would be significantly high. And is 252 when significantly high? Yes. So it was yes by the other method, and it's still yes by this rule because 252 is greater than 251.4. So either way, it turned out to be significantly high. Don't forget you can use the actual probability being less than 0.05 as well. Don't forget to look at the other video on how to use StatDisk as you're working through these problems. If you have any questions, please let me know.